let A and B be sets, and f from A to B be a function, and y1 a subset of y2 a subset of B. Next, think about what you want to show. Here's what you want to show. How do you prove a thing is a subset of another? What does it mean to be a subset? Yeah, so if you want to show this set is contained within that set, what do you need to prove?
Some arbitrary value in the smaller one is in the bigger one.
Yeah, you need to show that everything in the smaller one is in the bigger one. That means you need to prove a universally quantified statement. You need to prove everything in f inverse of y1 has a conclusion. Whenever you want to prove that everything in y1 satisfies some conclusion, let's consider any element of y1, any element of f inverse of y1, sorry. What name should I give this something?
I like X.
And whether or not this is part of what you write in your proof is, whether or not you want it. We must show that, what is it that you need to show? What's your goal going to be?
X is in F inverse of y2.
Cool. So especially like in a time setting like a quiz, one of these benchmarks, start with that. When you want to start your proof, start with your assumptions. Give the setup that's going to be like the logical structure that your proof is going to have. Now, well, I guess you gotta start just trying to do it. And how do you pull that off? Well, do you know what it means to be in the preimage of y1? If you don't, then you're fucked. Right? If you don't know what you know, then there's no way you can prove anything. You don't know what the definitions are. So, if you don't know what it means to be in the preimage, well, you have your notes, right? What's it mean to be in the preimage? Yeah. Cool. And that means that this x is an input, and when you apply that input, f to that input, you get something in y1. That's what it means to be in the preimage. So since x is in f inverse of y1, you get to conclude something. You get to know that f of x is in y1. That's the definition of preimage. Whenever someone tells you a thing is in the preimage of a set, they're telling you that when you apply that function to that input, you get into that set.
Can we now just say that f of x has to be in y2 because y1 is a subset of y2?
So f of x is in y1 because y1 is a subset of y2. I like that. And that seems like a full sentence.
Can we put y2 in f of x?
Yep. Which is, I believe, exactly what you said. All right, cool. That's nice.
Now can we take the inverse of both sides if you say x is in f inverse of y1?
Essentially, yes. But I don't like the idea of taking the inverse of both sides because f inverse isn't a function. I don't know that f is bijective. Instead, let's use this. This goes both ways. When someone tells you X is in the preimage, that means F of X is in the set. If you know an output lands in a set, that X needs to be in the preimage. All right, that seems pretty good.
So we've done it.
So we've done it, but let's get a stronger conclusion than so we've done it. What is it that you have done?
Can we just say, like, we've shown that for any x in the pre-image of y1, that x is in pre-image of y2?
Yes, I like that a lot. And let's have a really strong conclusion. You better conclude the thing that the theorem says is true.
Thus, the pre-image of y1 is a subset of the pre-image of y2.
Cool. So what's the takeaway here? When you're asked to prove some statement, like the start, you know what to do. Give the assumptions. Then think about what your goal is. In this case, you wanted to prove a subset statement. How do you prove a subset statement? You consider something in the small R set, and you know what you need to do. You need to show the thing in knowledge. We must show that X is in the big R set. Whenever you're asked to prove some set containment statement, that's how you should start. You can put your brain on autopilot, write that. Then, going between those two things, I don't know, start by thinking about definitions. So, if you didn't already know what the definition of the preimage is when you got to that point, well, you better look up some definitions. What does it mean to be in the preimage? And then start messing around, think about what you know, try to go from what you have to something. Hopefully, eventually you get to the desired conclusion. Cool. People feel a little better about that? Nice. A problem pretty similar to this, like a similar flavor question, something involving image, pre-image, maybe like set containment, maybe intersections and unions. I'm going to ask that on Monday. I've decided what I'm going to ask, but it's like written down somewhere else, so I don't like have it with me. Feel okay? All right. I'm also going to ask you something about fields. Yeah.
I actually have a question about the course of the semester with those like mastery questions. If in theory I had failed like 4 of them, so I had 8 problems in the backlog, could I take extra time after class to do more of those problems, or am I still restricted to 15 minutes?
I'm not heartless, so the answer is we would discuss that in this circumstance.
Great.
I am absolutely willing to have you say, like, look, I've got a bunch of these backed up. Can I schedule a time to come in and just like do a bunch of them? And the answer is yeah, we'll schedule something. Right after this class ends at noon, right? I like to eat lunch at noon, so like I probably won't want to do that. I mean, I'm also not heartless, so yeah, I will go hungry. If that seems like the only way to do it, but that's not the way I prefer to. And don't worry about that until we have to. I have a plan if that happens, but let's just plan on that not happening. Neato. Let's talk about the thing on the schedule for today. All right, so like the whole group part of this like didn't actually really happen. I heard too much. I don't know how to get started, so I wanted to like talk through it. You know what? Here's what I think you should do on your own time. See if you can modify that proof we just did. to do the following. Replace those two with subsets of the domain. And delete that. See if you can prove that. Not homework, unless it is. I don't remember what I assigned for homework at this point. Let's prove something about, let's talk about the order of the real numbers. So what do we know about real numbers right now? Real numbers are a field. That means you can add, subtract, multiply, and divide, and those things behave the way they should. The order properties of the real numbers are what allow you to talk about one number being bigger than another. So let's start by just listing the axioms that give an ordered field. So an ordered field is the following. It is a field, makes sense, together with some non-empty subset capital P, which is given the name the set of positive elements of F, satisfying some conditions. P better be closed under addition. If I take two positive numbers, then what can I conclude? Prompted by that thing in bold.
This should be a positive number.
Yeah, what do you mean by they?
The two numbers added together should be a positive number.
Same prompt. What if I tell you that P is closed under multiplication? What is that telling you?
Same thing, that's multiplication.
Nice. I shouldn't be using this pen. This pen is not erasable. Very dangerous. The trichotomy law. Trichotomy is something that you'll hear a few different times in a few different contexts. Whenever you see someone say that some trichotomy law holds, they're telling you that exactly one of three things is going to happen. And in this case, here's the thing you should think of. There are three types of real numbers. There are positive numbers, and there are, what would you want to put in those blanks?
Positive, negative, I don't know.
I like that. Yeah, there's positive numbers, there are negative numbers, and there's zero. I guess grammatically then the way I was hinting towards that was nonsense. So the trichotomy law says that for every A in this field, exactly one of three things happens. Either A is positive, A is 0, or A is negative. And I don't have a symbol right now for negative, but what does it mean to be negative if you know what it means to be positive?
Inverse being positive.
For every element of a field, exactly one of the following happens. Either A itself is positive, negative A is positive, or A is 0. And there's one other condition I'm going to emphasize. Part of the definition is the set of positive elements is in fact non-empty. So let's walk with this. Notice this doesn't tell you if any number in particular is positive. I guess it tells you 0 isn't. If 0 were positives, then 0 would both be 0 and be in the set of positives, but the trichotomy law says exactly one of the following holds. But what's a number that should be positive?
1.
1. So if that's true, we better be able to prove it. Let's try to prove it. So let's try to prove that 1 is positive. I'm going to try to proceed by contradiction. So let's suppose for the sake of contradiction that 1 is not in the set of positive numbers. That seems like the type of thing you should assume if you want to prove that 1 is in the set of positive numbers? Yeah, cool. Well, since 1 is not in the set of positives, then by the trichotomy law, one of two things has to happen. Either negative 1 is positive, which seems pretty nonsensical, so we better get a contradiction out of that, or 1 is equal to 0. That also seems pretty nonsensical, but we'll have to see what contradiction we get. So we have two cases. In each case, we need to get a contradiction. Since P is non-empty, what's special about non-empty sets? contain things. So I can let P be an element of big P. And that will be useful. I have a thing to start with. So let's try to get a contradiction out of this. So let's see, P itself, I know that P is in the set of positives, so I'm going to put that there. And I know that 1 is equal to 0 in case 1. So 1 is equal to 0, so let's just see what we can do. P is equal to P times 1, right? Oh, but what is 1 equal to?
0.
So P is equal to P times 0. So what next?
It's equal to 0.
Oh, cool. So P is equal to 0. In fact, there's like, scolium is a word that doesn't get used as much as I think it should. An observation you can make that's a consequence of a proof, but not what you are trying to prove. I think we just proved that if 1 is equal to 0, then everything in your field is equal to 0. That's kind of cool. Anyway, so P is in the set of positives and P is equal to 0. I claim this contradicts the trichotomy law. Why?
Since then any P would have to be 0 instead of a positive number.
Yeah. This contradicts the trichotomy law since exactly one of these things is supposed to happen. We have 2 of them happening. Since P is in P and P is equal to 0, but the trichotomy law says only one of these can happen. All right, let's try to play the same game. -1 is in P. What can we do with that? Well, there's a hint there. By the closure of P under multiplication, if I multiply 2 positives, I get a positive. Do I have 2 different positives right now?
No. You have 4 positive and negative.
I know that that's positive. I'm in the case that -1 is positive. So, what conclusion can I make?
-1 is positive. It's supposed to be. Or -1 is.
-1 times P is positive.
Nice. I know that P is positive, I know -1 is positive. So, -1 times P, I'll put the parentheses just for emphasis, is in capital P, is positive. Let's mess around with this and see what we can do. What do we know about -1 times P?
Can we say it's equal to -P?
So, -P is in P, and let's see if we can find a citation for that. Hopefully something we've already proven, or at least already stated. That seems like a field thing, so let's look through the field properties. That one seems to have to do with like -1s. Yeah.
If P is positive, and well, we can't have both negative P is positive and P is positive trichotomy law.
Nice. You've skipped ahead of what I wanted to do. No, but let's go to that. So explain why this is a contradiction. It's a contradiction because of what you just said. So the trichotomy law says that both P in P and -P in P cannot both be true. So there's the contradiction. Let's just finish this up. This result that says that -1 times p is negative p. It's like right there. So that's theorem 2.1.5. Item 2. Groovy. So either way, we got a contradiction. So it must be that 1 is positive,
Yes.
which is what we wanted to show. Okay, cool. 1 is a positive number. These ideas seem fair enough? So all an ordered field is it's a field where you can make sense of what it means to be positive. And that's not what an ordered field should mean. An ordered field should mean that you can do inequality. Oh, but like, that's enough to do inequality. If you know what it means for something to be positive, then what should it mean for A to be bigger than B?
A minus B is positive.
Yeah, cool. Subtract B from both sides, that should mean that B minus A is bigger than 0. No, you had the right intention. Or maybe we were even just looking in the wrong spot. A is bigger than B if the opposite is true.
Oh, yeah.
And greater than, less than or equal to, what should that mean? Well, it says what it means in the tin, right? A is less than or equal to B if.
If A minus B is in B or in 0. Is 0.
Yeah, how about just A equals B?
Well,
No, but I got flipped again. A is less than B, so I want B minus A, not A minus B there. Cool. So, just by knowing what it means to be positive, we can make sense of what inequality means. So, an ordered field is a field which contains a set of positive numbers. If you have a set of positive numbers, you can make sense of inequality. And in fact, under these circumstances, inequality does all the things you think it should. So let's list some things that we think inequality should do. Oh, I know these would be things that are things that you know are true and we're going to prove some. Let A, B, and C be elements of a field where F is an ordered field. I know what inequality means by what we just did. If A is less than B, then what can you tell me about A plus C as compared to B plus C?
less.
In fact, do I need to speak through filling in the rest of those blanks? Nah. If A is less than B and B is less than C, this is the rule of transitivity. A should be less than C. We'll need to prove that. There's a trichotomy law for inequality. For any two real numbers, A and B, exactly one of the following hold.
Less than, greater than, or equal.
Less than, greater than, or equal to. Cool. So, this gives a strategy. Suppose you want to show that A is equal to B. If you can show that A is not less than B, and A is not greater than B, then you get to conclude that A is equal to B. And that's like a proper analysis argument. Like that's something an algebraist can't do. It's something you need analysis to do. Groovy. Multiplicativity. If A is less than B and C itself is positive, then how do A times C and B times C compare?
Less than.
Cool. What if C is negative?
Flip it.
Yeah, multiply by a negative flips inequalities. Squaring. If A is not 0, then what can you tell me about A squared?
Greater than 0.
Yeah, of course, right? We know. We'll prove like some of these. At least 4, 5, and 6 are left to you. Some subset of them are blocks. So I think we'll prove whichever ones, we'll do at least one of them and then we'll decide. Prove at least one of 1 and 2. So between 1 and 2, let's first decide which one would you like to talk through at first. Which one looks more interesting? Two. Hearing decision made. Let's talk about 2. The proofs will be like pretty similar, and there's been a lot of copy paste. Oh, this is like, it was not the original plan. I was supposed to be quiet and have you do it. You'll do the other one. Let's prove transitivity. So let's assume that A, B, and C are in F and give the assumptions. What do we get to assume?
A is less than B, B is less than C.
Cool. What do we want to show?
A is less than C.
All right. So these proofs will be done by translating back to the original definition and then using things about positive numbers. Because we don't know anything about inequality. The only thing we know about inequality right now is it's defined in terms of positive numbers. So A is less than B, so what do we know?
B minus A is positive.
I know that B is less than C.
C minus B is positive.
And let's also think about the want to show. This down here won't be part of the proof, but it's gonna like tell us what we want to show. We want to show A is less than C, so what do we want?
C minus A is greater, is A positive.
Yeah, cool. So let's underline some stuff. There's a thing I know. There's a thing I know. There's a thing I want. Getting between them is now, we just need to try some stuff. Okay, what do we know about positives? We have closure under plus, closure under multiply, the trichotomy law. When in doubt, don't worry about getting a particular result. Let's just try something. I know that A plus B minus A and C minus B are both positive. I'm just going to try something. Let's see what closure under multiplication does for me. I'll go ahead. I've got spare paper. So since I know A minus B is positive, I know B minus C is positive. So by closure under dot, A minus B times B minus C is positive.
I think those are
Oh, son of a diddly. Yeah. I mean, I guess it's too late for me to worry about that kind of concern. I think I've already dropped an F-bomb this period, haven't I? B minus A, C minus B. Okay. Well, let's just expand that out and see what it is, see if that helps us. So expand that out. B times C minus A times C minus A times B plus.
Is it minus A times C again?
Gosh, well, there's a handwriting issue. Right, because you know what I'm foiling. I'm using the distributive logic wise, that's foiling. B times C, A times C with a minus, B b squared, there's my issue. Plus ab. Well, does that look like it has much to do with what I wanted? I wanted to get like just c minus a, right? So that doesn't look useful. But that was because of closure under multiplication. What else could I use?
Addition.
Yeah, it seems more useful, right? Let's even just do it. But no one was like saying it, so let's see what closure under addition does. So that's telling me that b minus a plus c minus b is in the set of positives. All right. By algebra, how does that simplify?
C minus A is a positive.
Nice. And there's some like associativity, the like axiom of the additive inverse, axiom of the identity, but it's just by algebra now. Oh, is that what I wanted? Cool, let's do that. So by additive closure of P, B minus A plus C minus B is in P. So by field properties, and I don't care about which ones now, C minus A is in P. All right, that was the want to show. How do you go from here to there? Why is that what we wanted to show?
Because our rules for inequality is just, that's a set entity, you know?
Yeah, probably can use the word definition. By the definition of inequality, C is greater than A. A is less than C. Let's put it in the same order as I want it. And if you want to be more precise, I guess that's probably definition 2.2.3, but the definition of inequality is happy for me. Does that feel pretty good? Think you could do something similar to accomplish the proof of item 1?
Try.
Yeah, try it. you know, remember you have all of the like field axioms. So anything that like you know is not just algebraically true. What can you do with this?
You can simplify it to B minus A's in P.
Oh, cool. Is that something you know?
Yes.
Oh, so you have a proof. It's just like sketching.
I'm just wondering how you add C to both of these in your reverse order. Assumption that with like what applies the C is.
See that though? It says that from here to there in all steps.
See how we can.
Yeah, because then like how do you go from here to
Distribute negatives and minus
C minus.
oh, yeah, C minus C.
awesome.
That's what it is.
So then,
So you can say like by additive integers. A plus 3C plus C minus C is still P.
I don't like your assumption.
Then you can say that
We want to prove if this then
algebra P plus C
that's what
minus
you
J
want.
C P.
So you're like proving that cos
And then
of the like, which in this case is actually true, but it's
plus
C.
C
Okay.
minus parentheses A plus C. And since it's there, 2.213 to get us to A plus C is less than P out C.
That's like
We are proof
frustrating answer, but it's like you don't get to know whether something's a good idea until you try it. And it's, like no one's gonna die. Like you can just try stuff. Well, mathematicians, not like biologists who are trying stuff means you're injecting something into someone.
chemistry better. Chemists are funny with their and Nazi.
Really?
My his dad's a chemist and he like get all this chemistry training to be safe and everything. He's still like every single problem physically he's like, take my drug. All this like start mixing stuff. And it's like two brains of a chemist. Either you just mix random stuff and see what happens or you actually do all the math and here's what the physics. So alright, so do you want to write down the words? Yes. Okay, so
by additive,
start by definition, 2.2.3, A less than B implies that B minus A is Alright, and then by additive inverse.
So here's the tragedy of like a 50-minute time slot that is the class. I want to end with like something being written up here. So even though like I think everyone's got an idea and they're like writing something up, let's come together and like fill in these spaces. So let's write down this proof. What do I get to assume if I want to prove?
A is less than B.
You want to prove an if then, the if is the assumption. What's my goal?
So A plus C is less than B plus C.
All right. And now let's start doing stuff. So, I think most people have something like a proof written down at this point. So, just tell me what to do. By the definition of inequality, what does this mean?
B minus A is in P.
Okay. What next?
Maybe this is using the one-on rule, but can we say by additive identity B minus A plus C minus C is also in P?
I don't care about you citing though, I think,
Okay.
which field property you use at this point. By doing some algebra, B minus A, you said plus C minus C? Nice. You can add and subtract something. If you always have to go through by the axiom of the additive identity and the axiom of the additive inverse, everything's going to take forever. So don't do that.
Okay.
Okay, why is that helpful?
Because now I can say by algebra B plus C minus A plus C is in P.
Yeah, I'm going to say by commutativity because it's not ball bonds.
Okay.
And you're commuting. So what did you want to say is in C? In P?
B plus C parentheses minus parentheses A plus C.
Okay, so it is more than just commutativity.
Okay.
By some more algebra, that is in P. Okay, why is that good?
And then can we use definition 2.2.3 again to bring it back to inequality?
Oh, plus not minus. Groovy. People end up with a proof something like that? And notice, in order to come up with this proof, you probably didn't do it in that order. Like the way that you would want to come up with this kind of proof is start with the thing you know and think about the want to show. The want to show looks more complicated, so you've probably got more space to simplify here. Figure out what you want to show, you figure out that that's the thing you want to show. Oh, that has lots of space for simplification. This is the same as that. Oh, but that's just B minus A. You know that B minus A is in P, so you really come up with this proof backwards. Cool. So, that puts me, it looks worse than it is. I'm about a page behind where I think I want to be right now. But, that's life. I think I have one day in the schedule that says this day is like fudge room. So, starting on Wednesday as the next like lecture / discussion day, I might wind up with some schedule items pushed around. Maybe the homework that's assigned today will actually be due a week later than it's currently due, because today's Friday. Cool. So let's see, I've got my office hour, and homework's due today. Anyone planning on coming by my office hour to talk about the homework?
Probably. I like double check. Double, triple, quadruple check before I go to honest with you.
Yeah, I'm happy to even just like read your walk and tell you, oh, I want like a sentence here. Can you put a sentence there? And like, I'm not saying I take off the point for that missing sentence, but like I'm not grading it yet. So if you want me to read through it, give you any comments, do it. Yeah.
Question, so I have a class during your office hours today, is there any way we could still like get you to check my work by any chance?
Yeah.